Today we're going to be proving that x squared, x to the fourth plus y to the fourth equals z squared has no solutions. Now in order to do so, we're going to be using a couple of theorems as well as two lemmas. The first theorem we're going to be using states that the triple of x, y, and z of positive integers is a primitive Pythagorean triple with y even if and only if there are relatively prime positive integers m and m such that m is greater than n with m odd and n even, or m even and n odd, such that x is equal to m squared minus n squared, y is equal to 2mn, and z is equal to m squared plus n squared. Now, one of the two lemmas we're going to be using is if we allow a and b to be positive integers, then the GCD of a and b equals 1. Then, if the GCD of a and b equal 1, then the GCD of a squared and b squared is equal to 1. And the second lemma we're going to be using is if r and s and t are positive integers such that the GCD of r and s equal 1 and rs equal t squared, then there exists integers m and n such that r equals m squared and s equals n squared. Now going back to our Diophantine equation, we're going to be using a proof of contradiction. The method we're going to be using is contradiction. It's a method of infinite descent, which is a contradiction, a proof by contradiction that relies on the least integer principle, which deals with the well-ordering principle. Okay. Now, to start our proof, we are going to assume that this Diophantine equation has non-trivial solutions, meaning it has solutions that are not zero, where x, y, and z are positive integers, and without loss of generality, the GCD of x and y equal 1. Now, let's suppose that for x, where x of 0 is equal to x, we're now going to use y sub 0 for y and z sub 0 for z. These are a solution of our Diophantine equation x to the fourth, y to the fourth equals z squared, where x sub 0, y sub 0, and z sub 0 are in the set of positive integers, and the GCD of x sub 0 and y sub 0 equal 1. Now substituting our new x, y, and z into our equation, we're going to have that x sub 0 to the fourth plus y sub 0 to the fourth is equal to z sub 0 squared. This can be rewritten as x sub 0 squared, quantity squared, plus y sub 0 squared, quantity squared, is equal to z sub 0 squared, where the GCD between x sub 0 squared and y sub 0 is equal to 1. Remember, this is using lemma 1. We can state that x sub 0 squared, y sub 0 squared, and z sub 0 squared is a primitive Pythagorean triple. Now, this is because if we were to take prime p and divide that by x sub 0 squared, and prime p divide that same prime p by y sub 0 squared, then p x sub 0 and p divides x of 0 and p divides y sub 0, that would actually be a contradiction to our original claim that the GCD of x sub 0 and y sub 0 is 1. So going back to our original Diophantine equation, we can now apply theorem 1 to this. Theorem 1 will now give you the solutions that x sub 0 squared is equal to m squared minus n, y sub 0 squared is equal to 2nm, and z sub 0 is equal to m squared plus n squared. Keep in mind that the GCD of m and m is equal to 1. This is a set of solutions of our Diophantine equation. Now, let's take our first equation here, x squared is equal to m squared minus n, and set that equal to m squared. Our new equation will look like x sub 0 squared plus n squared is equal to m squared. Now, since the GCD of m and n equal 1, then the x sub 0, n, and m is a primitive Pythagorean triple. Since this is another Pythagorean triple, we can again apply Theorem 1. Applying Theorem 1 to our new Diophantine equation will give us x sub 0 equals r squared minus s squared, n equals 2rs, and m equals r squared plus x squared. Remember again, the GCD between r and s is 1. This is a set of solutions of our Diophantine equation of x sub 0 squared plus n squared is equal to m squared. Now recall, according to our theorem, m is odd and n is even, and the GCD between them, m and n, is 1. So with this information, we can also say that the GCD of m and 2n is equal to 1, because keep in mind that n is even. Okay. Going back to our first Pythagorean triple, we can plug in our y sub 0, that our y sub 0 was equal to 2nn. Okay, if we apply lemma 2, we can let m equal, and we know that m is equal to z of 1, z sub 1 squared. 2 and n equals w squared, where z1 and w are positive integers. We're going to use this information to show that n is a perfect square, okay? So we're going to let w equal to 2v, and we can do that because remember, it is even, okay? So w is 2n, and remember it's even, where v is a positive integer, and we're going to solve for v. Now v equals to w divided by 2, all right? So v squared is going to be w squared divided by 4. Our w squared is equal to 2n divided by 4. If we reduce that, we're going to have n over 2. But what is n equal to? N is equal to 2rs. Again, once we reduce that, we have that this v squared is equal to rs. So rs is equal to v squared, and the GCD between r and s is 1. So we're going to apply our lemma 2, and let r equal some integer x sub 1 squared and s equals some integer y sub 1 squared, where x sub 1, y sub 1 are positive integers. Now, since the GCD of r and s is equal to 1, then it follows that the GCD of x and y, x sub 1, y sub 1, is also equal 1. Because remember, r is equal to x sub 1, and s is also equal to s sub 1. Our new equation will look like this. Okay, we take our original equation. If we square those, we will have x sub 1 to the 4th plus y sub 1 to the 4th, which is simply just r squared plus s squared. All right, taking our information, that's simply r squared plus s squared. If you remember from our original Diophantine equation, m was equal to r squared plus s squared. And of one of our other solutions, m also equal z sub 1 squared. So if we set these two equal to each other, we're going to have x sub 1 squared plus y sub 1 squared is equal to z sub 1 squared, where x, y, and z are positive integers. Now, we have z sub 1 is less than z sub 0. Now, the reason that is we know that z sub 1, of course, is going to be less than z sub 1 to the 4th power, all right? But z sub 1 to the 4th power is equal to m squared. Z sub 1 to the 4th power, remember, m is just z sub 1 squared, so z sub 1 to the 4th power is equal to m squared. This, of course, is less than m squared plus once you add another integer to it, okay? So that's m squared is going to be less than m squared plus an integer, but this here, expression here, is equal to z sub 0, okay? So we have that z sub 1 is less than z sub 0. I'm sorry, z sub 1 is less than z sub 0. Now, if we continue to repeat this process, x to the 1/4 plus y sub 1/4 is equal to z sub 1 squared, we would create a new integer, z sub 2, which that integer would be less than z sub 1, which also would be less than z sub 0. Now, this is a process that can be continued on indefinitely. For each new equation, it will give you a new integer, which is less than the one prior to it. So z sub 0 would be greater than z sub 1, and z sub 2 would be less than z sub 1. So there would not be a minimal or least element to this, as we continually to produce new integers for this. This is contradicting the well-ordering principle. Since it contradicts the well-ordering principle, therefore, x to the 4th plus y to the 4th equals z squared has no solutions.